Welcome class 10. Today we are going to learn a very important topic, combination of resistors. This is very important because most of the problems will be coming in ICSE from this particular topic. So the resistors are combined in different ways. First of all, they are combined in series. Secondly, they are combined in parallel. And thirdly, in both the ways, in series as well as parallel. So why the resistors are connected in these ways, series or parallel, or in both the cases, are they have their specific purposes. So when the resistance of the circuit is to be increased, okay, they are combined in series. And when the resistance of the circuit is to be decreased, they are combined in parallel. Combination in series. In series means the resistance are kept this way. Okay. Resistance R1, R2, R3. If they are connected this way, then we say they are connected in series. Where you can see this is the source of energy, that is the battery or cell. Okay. Here the longer length represents the plus side and the shorter one represents the minus. So the current will flow from here, okay, and it will reach R1, then again it will pass to R2, then R3 and come back to the cell in the negative terminal. So you can see that there is a single path for the current to flow. Now since there is only one single path, so the current which will flow, okay, will pass through the entire resistance. That's why the current remains same or fixed, or we can say current I is constant. But over here, since the current is fixed, only it has one path to travel through. Here we can see that R1 has two terminals over here at this point, and at this point it is connected. Okay, and if we take the potential difference at this particular point and this point, then the potential difference for R1 will be different. Potential difference in the similar way for R2 will be different, and potential difference for R3 will also be different. That means potential difference for every resistance R1, R2 and R3 will be different. That means the potential difference across the entire circuit for R1, R2 and R3 will be different, but the potential difference for this particular circuit from here, from this end to this end, cannot be different. It has to be same. That means the potential difference across the terminal of the cell has to be fixed. Okay, so this potential difference from here to here, these two terminals, the potential difference remains same and fixed, but the potential difference across R1, across R2 and across R3 will be different. But if we add the potential differences of R1 across R1 and the potential difference across R2 and the potential difference across R3, if we add them, then the total is supposed to be the potential difference of the between the terminals of this cell. So we can say that potential difference across the entire circuit is equal to the sum of potential differences across the individual resistors. Thus we can say that the potential difference V, this potential difference V, will be equal to V1, the potential difference across R1, the V2 potential difference across R2, and V3 potential difference across R3. And if there were many other resistors also combined in the similar way, in this one, in the same way, okay, then the voltage, sorry, the potential difference would be like V1 plus V2 plus V3, and it would go on. All right. So in this case, we can say that V is equal to V1 plus V2 plus V3. Now we know through Ohm's law that V is equal to IR. Therefore, we can say that V1 will be equal to IR1, since I is same for all the three resistors. So V1 is equal to IR1. So V1 from here to here, V1 will be I, the current which passes through, times the resistance 1, IR1. Similarly, V2 will be equal to IR2 and V3 is equal to IR3. Now, if you take the case of only the three resistors, then we'll have V is equal to V1 plus V2 plus V3. Replacing the values of V1, V2 and V3 as IR1, IR2 and IR3, we'll get V is equal to IR1 plus IR2 plus IR3, where I is the same common term in all these three terms. Okay, so we can write V is equal to I common R1 plus R2 plus R3 within the bracket. Now again, from Ohm's law, since V is equal to IR, okay, so we can say that in place of this V, if you write IR, then IR will be equal to IR1 plus R2 plus R3. Thus, R will be equal to R1 plus R2 plus R3. So if R is the equivalent resistance for the entire resistors over here, if R is the equivalent resistance, then we can write that R resistance, equivalent resistance when it is connected in series S, will be equal to R1 plus R2 plus R3 and so on. Alright. So in series combination, the equivalent resistance is equal to the sum of the individual resistances. Okay. So this is the main formula. Please remember this. Resistance in series is equal to R1 plus R2 plus R3 and so on. If there are 5 such resistances, then it will be R1 plus R2 plus R3 plus R4 plus R5. Okay. Similarly, it will continue. As many resistances are there, that many values will be over here. So let's take an example how this is calculated. It's very simple. If the resistors of resistances 5 ohm, 10 ohm and 20 ohms are connected in series, then the equivalent resistance Rs will be equal to, just simply add this 5 plus 10 plus 20, the resultant is 35 ohm. Okay, so the equivalent resistance when they are connected in series will be equal to 35 ohms. Combination in parallel. So what will happen if the resistors are connected in parallel? Parallel means we know the parallel lines. Okay, so over here, let's look at the circuit. R1, resistance 1, resistance 2 and resistance 3, R1, R2 and R3 are connected in parallel. They seem like they form the parallel lines. Alright, and their terminal are connected over here with the battery. So over here this is plus, marked plus, and this is marked minus. So this is the potential difference between plus and minus is taken as V. Okay, and I is the current which flows from the positive side, reaches out at this terminal and gets distributed in R1, R2 and R3 as I1, I2 and I3. Okay, so over here if you see properly that resistor 1, 2 and 3, all these resistors are connected to this potential difference over here and here, which actually is the potential difference V. So the potential difference across the terminals of the resistors remains the same. So the potential difference across each resistance is same. Now the current which passes through gets distributed in these three resistors, and the current which passes through are different. So the current in different resistors are different and is inversely proportional to the potential difference. Okay, this current is inversely proportional to the potential difference that we have learned in Ohm's law. So the sum of the currents I1, I2 and I3 is equal to the total current I drawn from the source. That means, let's look at the figure again. See over here, this current, okay, which passes through the entire resistors in R1, R2 and R3 and comes back over here. This current is supposed to be same, but over here at this point it gets distributed differently. But overall the current which flows remains I, that is fixed. So I has to be equal to I1 plus I2 plus I3. Alright. So we get I is equal to I1 plus I2 plus I3, and if there are other resistors also combined in parallel, then they will be added over here. The current will be added over here in the similar way. Now again, V is equal to IR from Ohm's law. So I is equal to V by R. Okay. So I is equal to V by R. If you take R down there in the denominator, so I equals V by R. If this is the case, then I1 will be equal to V by R1. V remains the same, potential difference. So we cannot write V1 or V2 or V3. So V, the potential difference is remaining the same. Only what is changing is current is changing and the resistors are changing. So I1 is equal to V by R1. Similarly, I2 will be equal to V by R2 and I3 is equal to V by R3. So if we take the case of 3 resistors in parallel, then I is equal to I1 plus I2 plus I3. That will be equal to V by R1, because I1 is this, plus V by R2, this is I2, and I3 is V by R3. So over here, if you replace I also by VR, I also as V by R, then we'll get V by R is equal to, see, V is common, so V taken common, we'll get 1 by R1 plus 1 by R2 plus 1 by R3. Alright, so this V and this V, if we can cancel this, then you'll get 1 by R from here equals 1 by R1 plus 1 by R2 plus 1 by R3. So in general we can say that 1 by R equivalent resistance connected in parallel will be equal to 1 by R1 plus 1 by R2 1 plus 1 by R3 plus dot dot dot, means it continues up till you get the n number of resistance, that is 1 by Rn. Okay, if there are n number of resistance connected in parallel, then there will be this formula used. Okay, if there are 7 different resistors connected in parallel, then R1 by R1 plus 1 by R2 plus 1 by R3, it will go up till 1 by R7. So in parallel combination, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. Okay, in parallel combination, the reciprocal of the equivalent resistance means, the reciprocal means the invert. Okay, 1 by Rp. It's not directly the equivalent resistance, it's invert of this. Okay, inverse, that is reciprocal of equivalent resistance is equal to the sum of, all these are sums of what? The reciprocals of all the resistors. Okay, individual resistances. If you add them, invert them and add them, then you'll get the reciprocal of the equivalent resistance. All right. The equivalent resistance is less than the smallest resistance connected. See, the result when you add all this will be such a less quantity that if any of these values, the resistance is very small, the result after adding will be even smaller than that particular resistance. Okay, so that's why the equivalent resistance is less than even the smallest resistance connected. I'll explain this with an example. All right, so let's say that if the resistors of resistances 1 ohm, 10 ohm and 100 ohms are connected in parallel, then the equivalent resistance will be given by, this is the equivalent resistance Rp, okay, will be given by, see, 1 by Rp, the formula, okay, is equal to 1 over 1 by 1, okay, 1 by 10 ohms and 1 by 100. So if you simplify this, you'll get 1 by 100. So if Rp is down there in the denominator, in order to bring it in the numerator, what will we do? We'll take the reciprocal of this one. If you take the reciprocal of this value, then this also gets inverted. Okay, so Rp will be equal to 100 by 111. So this value is getting inverted, 100 by 111, which is equal to 0.9009 ohms. Okay, now this is the result of the resistors when they are connected in parallel, and the resulting resistance will be equal to 0.9009, which is even less than the smallest resistance, that is 1 ohm. Okay, the smallest resistance is 1 ohm, but the resultant is even smaller than this value, so 0.9009 becomes the equivalent resistance. Okay, even after using them as connecting them as parallel. So what we can understand from here is that whenever we need to decrease the equivalent resistance of the overall connected resistors, then we will connect them in parallel. All right. Combination both in series and parallel. So here this is there's a figure over here. You can see these two resistors of 1 ohms each are connected in parallel, and this one is connected in series. So why do we use the connection, why do we connect the resistors both in parallel and series? Is because we need suppose we need a particular desired resistance, and we don't have that particular resistance directly, so we can combine them in this way and we can get the desired resistance. Okay, so in order to get the desired resistance, sometimes the resistors are combined in parallel and in series both. Okay, so let's see what will result after these resistors are combined in this way. So over here there can be more than one series or parallel combination. So there can be plenty of other series combination also, or plenty of other parallel combination also in the same circuit. Okay, it depends on what what equivalent resistance is required. So for that particular purpose only, the series the resistors are connected in different way. So over here, let's see the first case when they are connected in parallel. Okay, resistors of 1 ohm each. So over here, resistance connected in parallel will give you 1 by 1. Okay, 1 from the formula and 1 from this resistors value. Okay, 1 by 1, which will be equal to 2. So if 1 by Rp is equal to 2, that means Rp will be equal to 2 by 1, sorry, 1 by 2. Okay, the reciprocal of 2 is 1 by 2, that is equal to 0.5. So if this value is 0.5 and if this resistance is 1 ohm, then in series connection the resistance will be equal to 1 plus 0.5, that is equal to 1.5 ohm. So in order to get 1.5 ohm of resistance, you don't have 1.5 ohm resistance directly, but you can use 1 ohms. Okay, in such a way you connect it with parallel or series, or combination of both series and parallel, and then you'll get the result as 1.5 ohm. So in order to get a particular equivalent resistance, okay, you can use the resistors in parallel or in series or in both the series and parallel. All right, so with this we come to an end of our video. If you have any queries, if you have any doubt, please let me know through your mails. Thank you.